SwayamPrabha. Digital India. Educated India.
Hello all. In this video we will be looking at the generally orthotropic material, and since we are looking at a laminar level, we can safely assume it to be under plane stress. So, for a generally orthotropic material we will show the relations between the stress and strain for a orthotropic material. So, we will continue from the previous video, where for a specially orthotropic material we showed the relations between the stress and strain related with this laminar stiffness matrix. And we also showed the relation between the strain and stress using the laminar compliance matrix. But in reality, it does not happen that every time we have these coordinates, the chosen coordinates exactly aligned with the material coordinate system. Sometimes there might be an angle between these the chosen coordinate systems and the material coordinate system. That is when we need to know how to transform these stresses into the new coordinates, and that is what we will be looking in this video. So, we will start by looking at a generally orthotropic lamina with an example. So, consider this cylinder. Let us say this cylinder is prepared by filament winding, meaning that there is fibers wound at an angle. Let us say these are the fibers. And now let us say these fibers are making at an angle of theta with the x axis. So, as you can see, there are two ways you can define the coordinate system. The one way of defining it is along the fiber directions, meaning let us say we are taking an element here, I could define this as the direction 1 which is along the fibers, and another direction perpendicular to the fibers. So, here the way we have defined 1 2 is the material coordinate system or the principal direction. But since we are looking at a cylinder, especially it is in a general practice, it is good to define another coordinate system which is more convenient to the body or the cylinder which we are looking here. Meaning, let us say if we define another coordinate system such as this, where we say the x axis is now given as x and the vertical axis as y. So, now we say this x and y are the new body coordinates. Since x and y we are chosen based on how the cylinder is lying. So, the axis of the cylinder let us say is parallel to the x axis and y axis is the perpendicular to the axis we have chosen, which is x and y. So, now you can see that there are two different coordinate systems, one to referring to the principal directions or the material coordinates, and x y which we are now calling it as the body coordinates. There are other ways of calling it non-principal directions or coordinates or the off axis loading. I think now it is clear for us that there are two different coordinate systems which is 1 2 referring to the material coordinates and xy referring to the body coordinates. So, now let us see what are the notations we will be using to when we talk about the stiffness matrix and the compliance matrix in the new coordinate system, which is the body coordinates. Earlier we have written the stress strain relations in the material coordinates such as sigma 1, sigma 2, tau 1, 2. This is written in terms of the Q matrix, which is the laminar stiffness matrix times epsilon 1, epsilon 2, gamma 1, 2. So, now when we try to write the same in the body coordinates, the notation we will use is sigma x, sigma y and tau xy will be written in terms of the transformed stiffness matrix. We will represent that with a Q with a bar times epsilon x, epsilon y and x. Similarly, we can also write the strain stress relations where we write the compliance matrix, but let us start with the material coordinates again. Epsilon 1, epsilon 2, gamma 1, 2 is written in terms of the compliance matrix S times the stresses sigma 1, sigma 2, tau 1, 2. Now, when we are writing in the body coordinate system, the way we will write is epsilon x, epsilon y and gamma xy is written in terms of the transformed compliance matrix S bar times the corresponding stresses sigma x, sigma y and tau xy. So, first let us write it here. Q with the bar is the transformed stiffness matrix and S with a bar is the transformed compliance matrix. Okay. So, this should give introduce you to this new terminology of Q bar and S bar, and for us we should be clear about which coordinate systems we are talking about, whether it is the material coordinates or the body coordinates. When this is clear, now we are in a better position to see what is the relation or how can we write these stiffness matrix and the compliance matrix. But before we go there, let us see previously what are the elastic constants we have used to define the stiffness matrix and the compliance matrix. There we have used these elastic constants E1, E2, nu12 and G12. But now when we are discussing about the transform stiffness matrix, we will again use the same elastic constants which are E1, E2, nu12 and G12, but in addition to that we also need to define the orientation angle theta. So, we need 4 plus 1, 5 constants is what we need to be able to write this transform stiffness and the compliance matrix. So, now let us start with stress transformation and see how we can write the stresses in the body coordinates. Now, let us first draw the coordinates, which is these are the body coordinates x and y, and then we also have the material coordinates 1 and 2. And here we should be clear about how we define the orientation angle theta. We are saying that this is the angle which goes from the body coordinate x axis to the material coordinate axis 1. So, it is going from x to 1. So, this direction is important because later when we are going from the material coordinates to the body coordinates, we should then take it as minus theta instead of theta. And now for us to draw these stresses where we bring in both the stresses in the material coordinates and the body coordinates, we will consider a wedge, which I think most of us are familiar when we were talking about these mechanics of materials or the solid mechanics. So, let us consider this wedge. With an angle of theta. So, this is the wedge we are getting from the infinitesimal element. So, let us consider that this is the infinitesimal element which is acted upon by body stresses sigma x, sigma y and shear stresses tau x y. Now, what we are showing is, if we take a part of this infinitesimal element, this angle is theta such that it now aligns with the material coordinates as well. Now, on this wedge let us show what are the stresses acting. So, on the vertical face we have this sigma x and the shear stress tau x y. But on the inclined faces, that is where we have the stresses coming from the material coordinates, such as here we will see the sigma 2 and on this inclined face we see the stress sigma 1. And what about the shear stresses? We see that this is the shear stress which are tau 1 2. Okay. Now that we have shown on each of these three faces there are two stresses, one normal and the shear stress. Let us see how we can relate this. For this we bring in the equations of equilibrium. We can start with the sigma fx equal to 0. So, we will write the equations of equilibrium. Starting with summation of forces acting in the x direction equal to 0. Since we need to find the forces, we need to multiply these stresses with the corresponding area. So, now let us see what is the corresponding area. So, on this right plane the area is simply dy times the unit depth. But on these inclined faces we see that the cross section area is dA times. So, for example, where we have the sigma 2, it should be dA times sin theta, and similarly this should be tau 1 2 times dA sin theta. But for this inclined face where we have sigma 1, there we have dA times cos theta, and here it should be tau 1 2 times dA cos theta. So, since we multiplied the stresses with the cross section areas, now what we have is forces, and now we should be able to write them in the equilibrium equations. So, now let us start with the right face. There is only one force along the x axis, we will write it as sigma x dA. And now looking at this sigma 1 terms, we see it is at an angle, it is not exactly horizontal. So, we need to take a component of it along the x axis, which happens to be sigma 1 dA cos square theta. So, we have another cos term coming because of the component of the force, and for sigma 2 we have dA times sin square theta. And we also have contributions coming from the shear forces, especially on the inclined faces, and both will be the same amount. So, we will have 2 times this is plus 2 times tau 1 2 dA times sin theta cos theta, all going to 0. Since we notice that dA is common in each of these terms, that can be removed, and then I should be able to write sigma x as sigma 1 cos square theta plus sigma 2 sin square theta minus 2 tau 1 2 sin theta cos theta. Fine. Okay. So, what we achieved here is we are now able to write this stress sigma x in the body coordinate all in terms of the stresses in the material coordinate sigma 1, sigma 2 and tau 1 2, and we have taken help of this angle theta. So, with the orientation angle theta and the stress components in the material coordinates, we are now able to write stresses in the body coordinates. We started with sigma x. So, using the same wedge, is there any other equation can we write? The answer is yes, we can now write for summation of forces in the y direction, sigma y going to 0. We can repeat the same procedure even for this second equation of equilibrium, where on the right face we have this component of tau xy making a contribution. Regarding these two inclined faces, again we see all those four force components do come in the equation. So, once we work it out, we can show that tau xy equals sigma 1 times sin theta cos theta minus sigma 2 sin theta cos theta plus tau 1 2 into cos square theta minus sin square theta. Okay. So, with this we are able to show what is the relation for sigma x and tau xy. What is remaining is sigma y. How do we get this the third component of the stress sigma y? For this we need to consider another wedge. So, now let us show another wedge where we can get this sigma y. So, now let us say I make another wedge something like this, meaning that let us say this is the angle theta. Then what are the stresses acting on this wedge? On the vertical face or the horizontal face, we have this sigma y and the shear stress tau xy. And what about these inclined faces? Here we have sigma 1 and the other inclined face we have the sigma 2 and then the corresponding shear stresses, which is tau 1 2. Like we did previously, we can now multiply all of these stresses with the corresponding cross section areas, and then when we apply the summation of forces in the y direction going to 0, that should give us the relation for sigma x, which is sigma y equals sigma 1 sin square theta plus sigma 2 cos square theta plus 2 times tau 1 2 sin theta cos theta. Okay. Let us try to get these three equations into a matrix form. So, what are the three equations we are looking at? We are looking at this sigma x, tau xy and sigma y. So, now if I write these in the matrix form, where now I write sigma x, sigma y and tau xy. This can be written in terms of a 3 by 3 matrix times the stresses in the material coordinates, which are sigma 1, sigma 2 and tau 1 2. And what are the components of this matrix? I can, looking at these equations, one should be able to write. We will write it as C square, where C stands for cos theta and S stands for sin theta. We will write it as S square minus 2 S C S square C square and 2 S C and lastly for the shear stresses we will write it as sin theta cos theta minus sin theta cos theta and cos square theta minus sin square theta. Okay. So, this is the 3 by 3 matrix or the transformation matrix which takes you from the material coordinates to the body coordinates. But here again I want you to pay attention on this axis or the definition by which we showed the angle theta. So, where is theta going from? Theta is going from the body coordinates to the material coordinates, right. This is what the positive angle theta means. But the way we have derived, we are going from the material coordinates to the body coordinates. So, how do we show that? So, we are interested in seeing the transformation going from the body coordinates to the material coordinate. For that we need to inverse this matrix. Once we inverse this matrix, we should be able to show this as sigma 1 sigma 2 tau 1 2 is written in terms of a 3 by 3 matrix times the stresses in the body coordinates, which are the sigma x, sigma y, tau x y. But how do we get this 3 by 3 matrix? We simply need to inverse this original matrix we have here. So, that turns out to be cos square sin square 2 sin cos and sin square theta cos square theta minus 2 sin theta cos theta times minus sin theta cos theta and plus sin theta cos theta, and lastly cos square theta minus sin square theta. So, this 3 by 3 matrix we will now call it as the transformation matrix T, because if you multiply these stresses in the body coordinates, then it takes us to the stresses in the material coordinates 1 2. Similarly, both these 3 by 3 matrices are related, since we already mentioned that T is the 3 by 3 matrix in the right side. The matrix on the left side is the inverse of it, which we will write it as T inverse. So, once we pre-multiply this transformation matrix with the stresses in the material coordinates 1 2, then we get the stresses in the body coordinates x y. Okay. So, on this slide we have showed you what is the transformation matrix for the stresses. So, how do we go from stresses in the body coordinates to stresses in the material coordinates? For that we use this transformation matrix T. And but if you already have the stresses in the material coordinates, you need to pre-multiply with T inverse to get the stresses in the body coordinates. So, with this we have made progress in the sense like we are able to go from one coordinate system to the other coordinate system for stresses. Now, let us see for strains how we do the same. So, we will see that similar to what we have learned for the stresses, we can also apply for the strains. So, previously we are saying if we can use this transformation matrix to go from the body coordinates to the material coordinates. Okay. I can use the same transformation matrix for the strains as well. But here there is some attention we need to pay, because these transformations are only possible for tensorial quantities. So, when we define strains in the tensors, we can still use the same transformation matrix, but you might recall that we had made a distinction between epsilon 1 2 and gamma 1 2, where we said epsilon 1 2 is the tensor strain and gamma 1 2 as the engineering strain. So, the point we are trying to see here is we cannot be using the engineering strains and expect to use the same transformation matrix T. Since we want to use this transformation matrix T, we have to stick to the tensorial notation. So, how do we write these tensorial notations in the body format? We will write it as epsilon x, epsilon y, and instead of writing it as gamma xy, we will take half of it, which is then the tensorial quantity. So, gamma xy by 2. Then we are fine, because now we have written these strains in the tensorial notations. Similarly, let us write the strains in material coordinates. So, it will be epsilon 1, epsilon 2 and gamma 1 2 by 2. Since I have taken the half, now it is again in the tensor quantity. So, we resolve this problem by writing in terms of the engineering constants, but still be using the transformation matrix T. But we have got used to using these engineering strains gamma xy and gamma 1 2, and that is what we have been using when we have defined the stress strain or the strain stress relations. So, we should find a way where we can still go ahead and use simply gamma 1 2 without the half. To do that, we introduce a new matrix called Reuter's transformation matrix. Represented by R. So, the way it is defined is, you again have a 3 by 3 matrix with the diagonal terms 1, 1, 2 and the rest all zeros. So, looking at this matrix, you should appreciate why we have 2 in the last element, because now if I multiply this R with this matrix such as R times, let us say epsilon 1, epsilon 2 and half of gamma 1 2, this should give us the strains which we are used to, which are epsilon 1, epsilon 2 and gamma 1 2. Fine. Now, you can appreciate why we have this Reuter's transformation matrix written in this fashion. But sometimes you may also want to go the other way. So, for that let us define what is R inverse. So, how do we write R inverse now? It will be almost the same. The only difference is the diagonal elements will be 1 half. Instead of 2, we will replace it with half. The rest all again going to 0. So, with this R inverse, let us say the where I can use this R inverse is, so let us say I have these quantities written in terms of the engineering shear strain, meaning epsilon 1, epsilon 2, gamma 1 2. If I pre-multiply that with R inverse, then it should take it to the strains in the tensor form, epsilon 1, epsilon 2 and half of gamma 1 2. Okay. We will again start from this relation where we have strains both in materials and the body coordinates, but this time let us try to write it instead of the tensorial quantities, the engineering quantities. So, we will start with again the same thing, epsilon 1, epsilon 2, gamma 1 2 by 2 is transformation matrix T times epsilon x, epsilon y and half of gamma x y. But this time we will bring in this Reuter's transformation matrix R to rewrite the left side of this equation. So, this time to write this left side of the equation, I can use this expression, where I need to pre-multiply both sides with R inverse and write these strains as engineering constants, epsilon 1, epsilon 2 and gamma 1 2. And for the right hand side, we retain the transformation matrix T and replace this vector written in terms of tensor format to the engineering format, where we introduce this R inverse times strains epsilon x, epsilon y and gamma x y. and lastly if I pre-multiply both these sides with r, then it takes the form as epsilon 1, epsilon 2, gamma 1 2 can be written as r times T times R inverse times the strains in the body coordinates. So, this should give us the expression for the transformations of the strain. So, where let us say we know the strains in the body coordinates, we can use this expression to go to get the strains in the material coordinates. And of course, we can do the other way as well, we just need to inverse this equation to go from the material coordinate strains to the body coordinate strains. So, we have looked at the transformations for the stresses and we have now looked at the transformation for the strain. Now, let us use this information to see what is the relation between the stresses and strains in the body coordinates. So, here before we start let us bringing the important equations which we need. So, since we are more interested in the body coordinates, but we start this from the material coordinates. So, how do we write the strain stress relations? So, first let us write the stress strain relations in the material coordinates sigma 1, sigma 2, tau 1 2 is written in terms of this stiffness matrix Q times the strain in the material coordinates. But before we proceed, we will now bring in the stress transformations and the strain transformation. So, what did we learn in the stress transformations? There we showed that epsilon 1, epsilon 2 and tau 1 2 is written in simply as T times the transformation matrix times the stresses in the body coordinates. Similarly, what did we learn from the strain transformations? There we learned that the strain components epsilon 1, epsilon 2, gamma 1 2 can be written in terms of the strain components in the body coordinate system epsilon x, epsilon y, gamma x y using the relation r times T times R inverse. In fact, from linear algebra we can show that this expression of R, T and R inverse is nothing but the transformation matrix T inverse with a transpose. So, which means the same thing I can write it as epsilon 1, epsilon 2, gamma 1 2 is inverse transpose to the transformation matrix T times epsilon x, epsilon y, gamma x y. So, let us name this as expression 1 for the stress transformation and this as 2 for the strain transformation. Now, let us plug in these transformations into these stress strain relations. So, for the left hand side we can now rewrite it as T times sigma x, sigma y, tau x y is written as we will rewrite Q and then replace these strain components with T inverse transpose times the strains in the material coordinates. If I pre-multiply both these sides of the equation with T inverse, then we get the stresses sigma x, sigma y, tau x y as T inverse times Q, which is the stiffness matrix, times T inverse transpose times the strains in the body coordinates. So, this should be the final expression we are looking for. So, this is an expression which relates the stresses and strains in the body coordinates. But earlier we had an expression saying that we will use the transverse stiffness matrix as Q dash. So, we said Q dash is the transform stiffness matrix. Then looking at this expression, we should be able to say that this Q dash is equal to T inverse Q T inverse transpose. This should give us the transform stiffness matrix for stress strain relations in the body coordinates. So, here we have seen the stress strain relations in body coordinates, but we could also write the strain stress relations. Again in the body coordinates. For that, what do? We simply inverse this relation, or in other words we will simply write strains epsilon x y and gamma x y as the transformed compliance matrix, which we said we will represent it as S with a dash times the stresses sigma x, sigma y and tau x, where we said S bar is the transformed compliance matrix. Okay. So, this should summarize what we are looking for, which are the stiffness and the compliance matrix in the body coordinates. So, let us summarize what we have discussed in this video. We started with defining what is a generally orthotropic material, where we said we define in terms of the body coordinate systems. We said something is a body coordinate system when the orientations are different from the material coordinates or the principal directions 1 and 2. So, we represented it with x and y. And then we started looking at what is the stress transformation going from the one coordinate system to the other. Going from the body coordinates to the material coordinates, we have used this transformation matrix T. So, stresses, so T times the stresses in the body coordinates gave us the stresses in the material coordinates, or let us say if we start with stresses in the material coordinates, we need to pre-multiply with T inverse to get the stresses in the body coordinates. And similarly, we also wrote it for the strain transformation, but we realized because of the differences in the tensorial definition and the engineering definitions of the strain, we need to introduce this Deuter matrix, then only we should be able to use this transformation matrix T. But once we have looked at the stress and the strain transformation, we have taken advantage of it, and then we were able to derive what are the stress strain relations in the body coordinates. So, we were able to define or derive for the transformed stiffness matrix as well as the transformed compliance matrix, which we define as Q dash is the transformed stiffness matrix and S dash is the transformed compliance matrix. So, with this we are in a good position to go from one coordinate system to the other in terms of stresses, strain and those relations. So, this should help us to solve some real problems, and I advise all of you to pick some problems from standard books and solve a few, because then you will be more familiar with this theory and the you will appreciate how this theory can be applied to solve some practical problems. So, with this we will conclude.